In this lecture, we will discuss further on the shock expansion theory, and we will also discuss about flow through a converging diverging nozzle. We recall in the last lecture, we discussed about the shock expansion theory. We introduced it for the simplest possible geometry, that is a flat plate at an angle of attack to a supersonic free stream, and then we looked at the flow structures, the shocks, the expansion fans which we are developing, the pressure distribution which was uniform on the upper and lower surfaces, consequent forces which are generated starting from the resultant force, and then we moved on to work out lift and drag. So, this was the resultant force, and it came from a uniform pressure distribution both on the upper and lower surfaces of the flat plate. Moreover, we recall that we had attached straight oblique shocks, which means that the flat plate was not at a significant angle of attack, which would make the shock get detached and move away and become curved from the flat plate. In such a situation, the calculations would become much more complicated, and a simple theory based on straight oblique shock and expansions would not work. So, we are working within the purview of small deflection angles. Let us look at another geometry which is very commonly used in supersonic flow applications. Aircraft wings operating at high speeds. Let us say a supersonic flow is approaching this geometry, which we can call as a diamond wedge airfoil, and you are purposely keeping the angle of attack to be 0. That means, you will have a symmetric flow on the upper and lower surface, and there will be net 0 lift produced, but there will still be a wave drag produced. Keep that in mind. Again, assuming that the deflection that is produced is lower than the maximum deflection permitted for that free stream Mach number. Let us say this is the maximum thickness of the diamond airfoil. At the mid chord, as you can understand, there will be an expansion. The surface is deflecting away from the flow, and again here the flow gets compressed when it reaches the trailing side. So, there are a pair of oblique shocks because of the compression, because the flow is turned into it, while there are a pair of expansions where the flow is turning away. You can try proving for yourself that drag per unit span for this flow field problem would be given by this expression. Let us mark the regions 1, 2, 3. Remember that we will have uniform pressures in region 2 and 3 on the upper and lower surfaces of the diamond wedge airfoil, and they would be also identical on the upper and lower surfaces because of the symmetry of geometry and alpha equal to 0. So, you can try this problem at home. The problem gets a little more difficult when instead of the flow approaching at 0 degrees, you now have alpha, because then the shock structures or the expansions will become asymmetric, and then you will have a resultant force which will give rise to both lift and drag. So, that is a little more complicated problem. which is for alpha not equal to 0 degree. So, that can also be tried at home, but you can now start using some actual numbers. Let us say you take a value of m 1 equal to 2 or m 1 equal to 3, take a value of theta equal to 2 degree and take a suitable length of this airfoil. You can do the calculations based on C parametrically or just assign a certain value C equal to say 10 centimeters and work out the values of pressure, work out the values of forces, etc. So, this is a homework problem that you can try for yourselves. Let us move on and let us discuss about quasi one dimensional flow through a converging, diverging, which often is abbreviated as CD nozzle. This is what we are going to look at now. And of course, we will see the flow to be subsonic somewhere, supersonic somewhere else. What have we learned before this? We have learned about two dimensional compressible flows. In what context? We have learned them in the context of Mach wave, oblique shock wave. We just finished discussing Prandtl-Meyer expansion. So, these are all examples of two dimensional flows. What have we learned in the context of 1D flows? We have learned sound wave propagation, we have learned normal shocks. So, now we are going to take a path which is somewhere in between. We are calling it as quasi one dimensional, that is, it is probably closer to one dimensional than two dimensional or higher dimensional. Under what situation and circumstances can we really have such flows? Let us draw two stream tubes. In one, the stream tube area remains invariant, that is constant. Area is constant. Here, stream tube area varies gradually along the flow direction. This word gradually is very, very important. This is a perfectly one dimensional case. Here we will say that this is going to lead to a quasi or quasi one dimensional flow. This is a pure one dimensional flow, while the other is a quasi one dimensional flow. Here the cross sectional area A is constant. Therefore, the properties will also not vary along x. Here A is a function of x, but it changes gradually with x, and therefore, though strictly speaking the properties will also start varying gradually in the other two dimensions. So, if it is Cartesian, then a change of area in x will trigger small changes in flow properties even along y and z, not only along x. If you look at velocity, for example, a small change in area will induce small velocity components v and w along with changes in u. But here we are neglecting the changes along the other two directions, saying that gradual changes in area will not trigger those multidimensional changes, and that is precisely the purview of quasi one dimensional flow. So, keeping this assumption in mind, let us go ahead and try to work out the conservation equations, and then from there let us see how we can take it forward. So, if we are looking at that stream tube, then we know that as we move along that stream tube, the product of rho u a, that should be constant, that we have learned from our continuity equation. right. So, if that remains constant, let us try to rewrite it slightly. We will write it like this. Say we take a natural log of the two sides, let us call this C. So, it is log C, and log rho u a will be log rho plus log u plus log a. Now, take a differential. So, if you take a differential, how does it work out? You get a 1 by rho d rho. So, that is d rho by rho plus d u by u plus d a by a. This is density, this is velocity, this is cross sectional area. And if you take a differential of this, because it is a constant, it will go to 0. So, this is the continuity equation written in a slightly different way. Now, let us take a small section, a differential thickness section of that quasi one dimensional stream tube. Let us try to draw it here. It has a small length, say dx, and the area has changed by a very small amount, you can make out. So, these shaded regions are responsible for the area change, and let us say we are taking just unit span or depth, and therefore, we can just deal with those lengths and quantify the area change. So, let us say this cross section is A and the other cross section is A plus d A, and the d A comes from those shaded portions. Let us mark P, rho, u, etc. on the left hand side. Let us call this as say station 1, the other one station 2, and there will be differential changes in all those flow properties, because you have moved a small distance and all these properties are functions of x. And therefore, they are certainly going to change once you have moved them through a distance dx. Now, if you recall about the equation for momentum conservation, how will it work out? Let us try to figure out. We know that momentum conservation will come from the original equation that we have from the control volume approach. Let us try to write that down. We are writing it for the x component. So, when we apply it to this control volume, how does it work out really? If you had applied it to a general control volume, let us say which has a finite extent, then how would it work out? You would have two different stations with significant changes in properties etc., because it is no longer a differential one. And let us mark a small element on the side faces of the control volume. Let us say we call it ds. You will see that what will the left hand side contribute? The left hand side will contribute minus rho 1 u 1 square a 1 plus rho 2 u 2 square a 2. That is precisely what is going to come from here across the two sections 1 and 2. Okay. Where of course, u 1 is here, which is pointing into the control volume, while a 1 is pointing out. So, vectorially this is how you represent, and because they are pointing in opposite directions, there is a negative sign here, while in the other side a 2 points out, u 2 also points out, and therefore, you get a positive quantity there. What about pressure? on the right hand side? Well, pressure has two contributions. One is what you see across these two faces, but there is also going to be a contribution from the curved side. Let us see why. So, let us first write out for the two faces. The two faces will contribute minus P 1 A 1 plus P 2 A 2. All right. So, again pressure force has a negative sign wherever the pressure and the area vector are pointing in the opposite direction, that is here. Now, let us look at the curved side. On the curved side, you have a contribution coming like this. What is this dA? dA is the x component of the vector ds. The ds vector has an x component because it is not pointing normal to the flow direction. It has a tilt and therefore, it has a component along x. It does not have a component only along y, but it also has a component along x, and this dA is that component that we are talking about. All right. So, that will have a contribution like this, and it will be based on the area change between the sections 1 and 2 and the pressure which is acting on the curved surface. So, this is how there are two contributions, one coming from the faces at inlet and outlet of the section, while the other is coming from the curved side. So, if we understand this, it will be easier for us now to apply it to this differential control volume. So, let us try to write down that equation for this differential control volume. If you apply it across the two sections, what do you get? You get an equation like this. How does it compare with the case that we were just looking at, where finite changes are involved? It will be easier for us to understand if we write that equation more systematically and compare with what we are writing now. So, if we had written that equation down for the finite sized control volume, once again it would look like this: an integral between a 1 to a 2 p dA is equal to p 2 a 2 plus rho 2 u 2 square a 2. So, this would be the equation you would obtain for a finite control volume. Notice that integral p dA term here becomes much simplified. It is just p times dA, and it is the pressure times that change in area which is working out for the differential control volume. Other terms of course are easy to understand. For example, this term, it corresponds to this summation, while these two terms correspond to these two terms here. Okay. So, once we are done with that, let us try to simplify. We would do a simplification in the sense that we neglect higher order terms, higher order in the sense product of differentials. So, if you neglect that, what do you get? You get a very familiar equation, that is simply Euler equation, which we have visited earlier, but following a different approach. How can we use this equation together with the continuity equation? Let us try to take it forward. So, we will rewrite Euler equation like this: dP by rho is minus u du, and the dP by rho can be written as dP by d rho into d rho by rho. Remember that d rho by rho is one of the terms in the continuity equation also, and this is familiar to us, dP by dP d rho. You remember that under isentropic conditions, this gives you the square of the sonic speed. Are we having an isentropic flow here? Yes, if we are not dealing with shocks. So, for now we will have no shocks. We do not want to deal with shocks immediately. We are talking about an isentropic flow through the nozzle. In that case, we can rewrite this as a square d rho by rho. So, what do we have finally? We have d rho by rho equals minus u du by a square, which finally boils down to this. Now, you look at the continuity equation which you had derived earlier, plug this result into it, what will you get? Plus dA by A. This is what you are going to get from the continuity equation. If you rearrange, what will that give you? It will give you a very important relation used for quasi one dimensional compressible flow. This is what is called as the area velocity relation. Why is it so very important? Because it is going to tell you that as you change the area of that stream tube, then how is the velocity going to change depending on the local Mach number of the flow. We have not been talking about the Mach number of the flow very often over here. Now, let us try to look at it from that direction, that how Mach number starts playing a role over here in the area velocity relation. Let us say if you are talking about a subsonic flow, then what will dA by A give you? It will give you some constant k with a minus sign, where the constant k is greater than 0. We will introduce another constant L, that is why we are marking both of them to be positive constants. So, what do you notice? You notice that this has a negative sign while this has a positive sign, while the constants themselves are both positive. What is the implication that comes out of this? It is a very profound implication which comes. What is it? That if area decreases, velocity increases, and which also means that when area increases, velocity decreases. Well, this is not a very surprising result, because this is what we had seen for incompressible flow also. So, as long as the flow is subsonic, this is what is going to be seen, while the finding is quite surprising in the other case. If area decreases, velocity decreases if it is a supersonic flow. If area increases, so does the velocity. That means, if you take a flow through a converging passage, u is going to drop. If you take it through a diverging passage, u is going to increase, which is quite surprising, but that is what this relation tells us. So, in the supersonic world, it could be a little counterintuitive. What happens at Mach 1, that is sonic condition? dA basically becomes 0, that means the area is not changing, even though du is finite. Such a situation can still arise. So, if you look at the mathematics, it can mean both a maximum area or a minimum area, but in a physical world we see that it happens to be a minimum area situation only, which is permitted for the sonic condition. Let us say you are trying to accelerate a flow from a subsonic condition to a supersonic condition. You are using a CD nozzle for doing that. How does it help? It has a converging section. So, a subsonic flow will be accelerated. Let us say it reaches the minimum area, which we will call as a throat, because that is the narrowest section, and let us say we achieve sonic condition there. Now, going by our understanding, if you increase the area beyond that, the flow is going to accelerate, and therefore, you have a supersonic flow. What is this called? It is called as a supersonic nozzle, used for accelerating a subsonic flow to a supersonic condition. On the other hand, let us say you are bringing a supersonic flow to a sonic condition here and then providing it with a diverging section, it can slow down to a subsonic flow. So, that becomes a supersonic diffuser. So, in both cases there was a throat, a minimum area section where the Mach 1 condition was achieved, but in one case a subsonic flow accelerated to a supersonic condition, in another case a supersonic flow decelerated to a subsonic condition. There is a very important relation which you can derive further, which is called as area Mach number relation. Which looks like this. What does it tell you? This gives you what is called as a area ratio. So, let this be a duct. If you are achieving Mach 1 condition at the throat, you have what is called as the A star here, because that is the sonic condition. You look at any other section, it can have a area A. That same area may exist on the other side of the CD nozzle. And let us say you are having a subsonic flow while you have a supersonic flow here. That means, for an isentropic flow through a CD nozzle, there are two solutions. One happens to be a subsonic solution, the other happens to be a supersonic solution corresponding to a particular area. So, the same area on the two sides of the throat gives you two different Mach numbers. You can write down this relation by changing the dependent and independent variables like this too. So, in that case you can figure out that this is how the solution comes out, that for a particular area ratio there are two values of Mach number which will be obtained. Let us suppose you are trying to establish a flow through this nozzle by altering the exit pressure or back pressure. So, this is the exit plane. Whatever pressure exists beyond it can be the exit pressure or the back pressure. And let us say you are starting the flow by feeding this from a large high pressure reservoir where the flow is nearly stagnant. which means the pressure over there is P naught, temperature T naught, density rho naught and so on nearly. And then if there is a pressure difference between the reservoir and what you have at the exit plane, then the flow can start as long as the exit plane pressure is lower than P naught. So, let us say you are operating a valve downstream or you are running a vacuum pump downstream, so that you can create this pressure difference between the two sides. Gradually a flow starts and the mass flow rate that moves through the CD nozzle also begins to increase. It increases up to a point where sonic conditions are reached at the throat of the CD nozzle. Beyond that, the mass flow rate does not change anymore, because the dimensions that you have reached are the minimum dimensions which are available in that CD nozzle, and also you have reached sonic condition. So, you cannot have a Mach number going beyond the sonic condition at the minimum area. So, at the minimum area, that is the throat area, if you have reached sonic conditions, you cannot increase the Mach number further at the throat for an isentropic flow. So, what we were saying was that if you plot the m dot versus the change in exit pressure. So, when the exit pressure is plotted along the horizontal, there is 0 mass flow rate if the pressure is P naught, then you are reducing the pressure and bringing it to some other pressure over here. We will call it P E3 for now. At that, the maximum mass flow rate is reached, and if you keep reducing the pressure further, the mass flow rate will not change anymore. So, this is what is called as choking of the flow. That means, maximum mass flow rate has been reached. So, beyond that, even if the back pressure is reduced, there will be no change of the mass flow rate. Okay? And if you were to look at the Mach number variation, for example, through the tunnel at inlet, throat and exit, this is how the Mach number would change gradually till it reaches sonic condition at the throat. Every time maintaining subsonic condition in the downstream side. So, as you can see that only at the throat Mach 1 has been reached, and that is this point. Corresponding to that, we will mark a pressure here for which it has been reached. So, you can mark two different other pressures, say P1, PE2, for which these Mach numbers have been achieved, and every time you have a subsonic flow here as well as a subsonic flow here upstream, but you just have a sonic flow for PE3 back pressure at the throat, and that is where the throat gets choked. If you reduce the pressure at the exit any further, there will be no change in the way the Mach number varies in this section. So, that part of the flow gets frozen essentially. This flow remains frozen for further reduction in exit pressure or back pressure. So, in this lecture we discussed further about shock expansion theory. Subsequently, we discussed about flow through a converging diverging nozzle under different conditions which produce isentropic flow. We could not complete our discussion on non isentropic flow, which we will do in our next lecture. Thank you.